nanohub.org.
Online simulation and more for nanotechnology.
All right, so now we're going to start a new topic. We go back basically to coming up with prior distributions for things that are uncertain, but today we're going to focus on uncertain things that are functions. And I'll explain that a little bit later. Anyway, so I'll go through a quick reminder, then I'll tell you about this idea about how you can describe your uncertainty about a function. First of all, I'll try to motivate it and show you where uncertain functions appear in real applications. And then I'll tell you about this tool called Gaussian process, which is basically the description of a probability measure in a function space. And we'll try to do it as simple as possible. And I'll show you how to sample functions from such a probability measure, how to describe your uncertainty about a function, and then how to sample from that distribution. And this is going to be, what we're going to talk about today is going to be the basis for pretty much all the uncertainty propagation stuff that we're going to do later on. We're going to be propagating these uncertainties through other models, all right? Now, it just happens that this thing, Gaussian processes, you can also use them to do regression, and I'll talk about that in 2 lectures, okay? But this is like a side thing that we're going to be able to do once we understand what Gaussian processes are. Anyway, as a reminder from before, we talked about regression, and again, about the basic ingredients: generalized linear model, likelihood that models the measurement process, prior on the weights. You have to put it if you want to be Bayesian, and then if you want to be fully Bayesian on whatever prior you put on the weights, if there are any parameters, you need to put a prior on these parameters. And this way of thinking is called hierarchical Bayes, okay? Or a hierarchical Bayesian model. Hierarchical in the sense that you build a hierarchy of distributions that describe your state of knowledge. Anyway, the right thing to do, of course, is to write down the posterior distribution of everything, the weights and all the other parameters, and characterize it somehow. Now, if you are lucky and this is Gaussian and that is Gaussian, then the whole thing is just going to be a Gaussian that you can easily estimate, and one of your homework problems is going to be exactly that. But if you are unlucky, it is not going to be Gaussian, and in most of the cases it's not going to be Gaussian. And then you need to bring into the picture advanced techniques like Markov chain Monte Carlo, variation inference, and these are going to be what we're going to work on later on in class. Okay. So we'll come back to this. We'll talk about the evidence approximation, which is again something that you do if you don't really want to use one of the advanced techniques. Okay, and I will explain how it worked. And we also introduced the idea of automatic relevance determination, which is basically very simple, a very simple idea. You just give to your model the ability to turn off some of the weights. That's all you do. So you go to, instead of putting the same prior on all the weights, you go ahead and you put a different prior on each one of the weights, and you give them some parameters that allow the model, by tuning these parameters, to turn off a weight, effectively eliminating the corresponding basis function from your model. And you're going to have the chance to experiment with this in the homework. Okay, so we have already posted the homework. It is due on the 15th, so you have basically a week for it. And there is a little bit of theory, deriving some of the equations that we did here in class, and then there are some more theory, okay? That theory about which we haven't talked in class, but I'll let you be surprised by problem 2. And then we have also 2 problems in which you just have to apply these ideas to data sets. One of the data sets is synthetic. And it's just how it gives you the chance to play with it. The other data set is from a real application, okay? Even though they're both like one-dimensional data sets. Anyway, so because it is impossible to do this homework on the last day, it is going to be impossible, trust me. Can't happen. You should start earlier, okay? So give it a few days. And the best way to start would be to read chapter 3 of Bishop and then get started with the homework. You will be happy about it if you do go through chapter 3 of Bishop, because you will find the solution of problem number 1 in it. Okay? Any questions about the homework? All right. Let's start now on the new topic, which is priors on function spaces. And we're going to introduce something called Gaussian processes, okay? And the best book for Gaussian processes is this book by Rasmussen and Christopher Williams, and the book is called Gaussian Processes for Machine Learning. It has way more than what I'm going to talk about today, but it's freely available online on this website, gaussianprocess.org. And you can read chapter 1, for example, and I'll give you some more references based on the book later, and you will need it when you do the homework based on this topic. And there is an excellent Python module that implements pretty much everything you want to do with Gaussian processes. And it's called GPy. Okay, it's by the University of Sheffield, by Neil Lawrence Group. Lawrence is one of the pioneers in machine learning nowadays. May have moved to Amazon, I'm not sure, but anyway, this is well maintained and updated constantly with the state of the art on Gaussian processes. And it's not just useful for what we're going to be talking about today. It's actually useful for doing other stuff like regression or classification tasks. If you want a truly powerful model that doesn't really use any basis functions, this is the place to go. All right. But today we're going to focus on coming up with the quantification of our state of knowledge about functions. Okay. We're going to talk about how uncertain we are about functions. So first of all, let's motivate the discussion a little bit. Why do we need probability measures on function spaces? Okay. Let me show you some examples. So this is an example from structural engineering. You have a building, and you have perhaps a structural model of the building, which is a finite element model describing the dynamics of the building. And that model requires us an input. For example, if you want to study the effect of earthquakes, an earthquake has on your structure, it requires us an input, the acceleration of the ground as a function of time because of the earthquake, right? So you need this, the ground motion, all right? So that ground motion, the acceleration of the ground as a function of time, is a function, obviously, of time, right? I just said it. And you don't really know how it's going to look like. Make sense? So you are uncertain about it. You cannot really, I mean, you can't even tell when an earthquake is going to happen, okay? Let alone, and of course, it goes without saying that you cannot really tell exactly what the acceleration of the ground is going to be when it happens, right? You don't even know if it happens, how long it's going to take. So you pretty much don't know anything about that function. I mean, there's still a lot of things that you can know, right? But the exact details of what is going to happen is unknown. So you may want to come up with a probabilistic model for the earthquake itself, right? You may want to come up with a model that spits out possible earthquakes, right? So you may want to ask the model the question, if an earthquake of magnitude 5 happens, how would it look like? Can you give me 1,000 samples of such earthquakes? Right? Does that make sense? Once you have come up with such a model, and you should really do your best to come up with such a model, think about it, of course, right? Use data, and so on and so forth. Once you have it, then you can propagate this uncertainty through the structural model and calculate, let's say, the probability that your structure exceeds a certain limit state that may be catastrophic in the event of an earthquake. Right? Here's another example. You may want to, this is from financial engineering. The uncertainty here is the price as a function of time of the assets that you may want to own or sell, right? Buy and sell or sell. So the price of assets like stocks or commodities or whatever is a function of time, and you cannot really tell what they're going to do, right? So you need a probabilistic model for these functions. You need a model that can give you samples of what the asset prices may look like, right? And once you have this model, then you can ask questions like, what is the portfolio allocation that maximizes the expected return subject to a given risk that you're willing to take, a variance, for example, or what is the portfolio that minimizes the variance if you are afraid of taking risk, and so on and so forth. But the key ingredient is, again, a probabilistic model on a function space, and the function space is the space of asset prices, right? And these are functions of time. All right? And what is currently used, Gaussian processes are used for this particular model specifically, okay? So the underlying model is the exponential of a special Gaussian process called the random walk with a drift. And of course it's wrong, okay? It's the wrong model. That's why we can't predict anything. But anyway, it is a model. It works very well when nothing happens. Okay. Anyway, so here's another example of a case in which you may have uncertainty in a function space. So imagine that you're studying an oil reservoir and you want to optimize the oil production, right? So you want to extract as much oil as possible out of the reservoir. And you want to, but you don't know two things. First of all, you don't know the price of the oil, right? So you may go back to the previous page and grab a probabilistic model for the price of the oil, right? Because if oil is very cheap, you may want to keep it in the reservoir. If it is expensive, you may want to take it out and sell it. So this is one uncertainty, but there's also another kind of uncertainty, and this is basically how the ground looks like. It is impossible to know exactly how a rock that is miles, tens of miles down, right, inside the earth, it's impossible to know exactly how it looks like. So you're gonna have to describe your state of knowledge about it somehow. Okay, and the way you describe it is with a function called the soil permeability. There are actually two functions, permeability and porosity. Permeability tells you how much, let's talk about porosity. Porosity tells you how much empty space there is inside the rock, and in this empty space there may be oil, right? So it's let's say a function of space that tells you how much empty space you have locally, all right, at different locations. So that function, you cannot really know it because it is impossible to measure it everywhere. You can drill, take the soil out and look at it. That's one thing you can do, but you cannot drill everywhere, right? There are the reservoirs that are as big as 2 or 3 counties, right? So you cannot possibly do that everywhere. And the other thing that you can do, of course, is you can look at the historical production of oil, because this is, I mean, you can describe what is going on there using fluid dynamics, right? You know the pressure with which you're pumping stuff inside your reservoir, and you can measure what is coming out. And from that history, if you have it like for 10 years, perhaps you can solve an inverse problem and characterize and come up with a model for the ground. So that's another thing that you can do. You can try to match historical data to come up with that model. But again, this is not, you're not going to nail it. There's going to be some residual uncertainty in there. And the other thing that you can do is you can hit the ground, you can blow up stuff and listen to the acoustic response and try to solve what is called as a seismic inversion problem. Basically come up with a speed of sound at different points on the ground, and then try to associate that speed of ground with the porosity. That's another thing that you can do. And that's pretty much all you can do, okay? Yes, okay. So this is another example from numerical weather prediction. So numerical weather prediction, the equations that can predict what the temperature field, the pressure field, the air velocity field is going to look like. It's basically fluid dynamics coupled with thermodynamics, and so some things happening in the atmosphere and input from the sun and all that. It's a complicated thing, but again, it's a set of partial differential equations. And what you need to make predictions is the initial conditions, and of course the boundary conditions, but usually we take the boundary conditions to be periodic. But anyway, we need the initial conditions, right? The initial conditions here means you need the velocity of the air everywhere on Earth, the temperature everywhere on Earth, and the pressure everywhere on Earth, if these are the only variables that are involved, to get started making predictions, right? And these initial conditions, you cannot really know them precisely. And so you have uncertainty about the initial conditions, which are functions. Okay? So you have, again, uncertainty about functions. It's a function of space this time, of 2D space. And this uncertainty is one of the uncertainties that causes problems when we try to predict, let's say, the path of a storm. Okay, one of the uncertainties. There are more uncertainties, right? One of the uncertainties is the uncertainty in the initial conditions. There are other uncertainties about which we're not going to talk in this class. Like, for example, the uncertainty induced by the fact that you're not really solving the partial differential equations exactly, but you're using a grid that is like 4 by 4 kilometers, which is huge. You're also discretizing in time. This is going to add more uncertainty. You're not solving it every millisecond, but for every hour or so. This is going to introduce uncertainty. And of course, there is more uncertainty. Namely, the model is definitely wrong. It ignores things. So this is one more source of uncertainty. All right. But initial conditions is one of the most important ones. Questions? Yes.
In the previous lecture, y versus x, even there, y is a function, y is a function of x-ray.
Mm-hmm.
How are they this different from that?
So now, in the previous lecture, we were talking about regression. Okay, a very specific problem. We had an x, observations of x and y, and we're trying to find a map. Okay. Now I'm getting away from that problem. It's a new chapter. Okay, new chapter. And my problem is this. You have a physical problem, and there is a quantity in your physical problem that is a function, okay? And you are uncertain about it. Make sense? Examples of that. You may have to do regression at some point to quantify this uncertainty, and we will see that in the next lecture. Okay, here's one more example of something uncertain. So here you have basically the statistical mechanics model, the Boltzmann distribution. Q is the degrees of freedom of the system. Anyway, a Boltzmann distribution says that the probability of finding the system at a given set of degrees of freedom is proportional to the exponential of this thing. And that thing over there, I mean, this is the temperature, right? And that thing over there is the potential energy of the system. And that potential energy is not actually known. Okay, what we typically do is we guess it. We guess its form, and then we calibrate the parameters to some data so that it can predict certain things. And guess what happens? If you calibrate to some data, then it doesn't predict other stuff. Okay? So typically what happens is that these potentials are not transferable. Now, in principle, you could get the right potential by solving the Schrödinger equation for the whole system, but this is impossible. Okay, it is actually impossible to do computationally unless somebody invents quantum computers. You cannot do it. The next best thing to do is to use an approximation of the Schrödinger equations, like density functional theory, for example, but that is also not right. You are actually introducing a little bit of uncertainty when you go from the correct Schrödinger equation to density functional theory. And that uncertainty will be represented there, okay? So you can have uncertainty, if you like, on a constitutive law of your model, right? You can have uncertainty in a physical law. Here, the potential energy of this system. In a mechanical engineering problem, the mechanics problem, you could have uncertainty in the stress-strain relation, right? Maybe Hooke's law is not, maybe, you are in the linear regime and you know that Hooke's law holds, but you don't know the Young modulus of your material. And maybe your Young modulus, because you have a heterogeneous material, varies with space. Okay? So that would be one example of inelasticity of having an uncertain parameter that is a function. And so on and so forth. Okay? Questions? Okay, my goal is just to show you that there are uncertain things that are functions. As a matter of fact, most of the uncertain things that you have in your models are functions. Okay? So, wrapping it up, some examples. External forcings of your physical models may be uncertain functions. Field parameters of your model, parameters of your model that depend on the location of a body or the location of ground, whatever, like the elasticity tensors, like the porosity of the ground in underground flow simulations, and so on and so forth. Initial conditions to partial differential equations are uncertain functions. Boundary conditions in partial differential equations are uncertain functions. And you can also have uncertainty in the physical laws themselves. All right? You may be actually uncertain about your model. And there is absolutely no end. All right? Yes?
How can you be uncertain about the physical laws? You're talking about the constants?
So,
Universal constants?
I'll give you an example, right? What is your major? What do you do?
Computer engineering.
Okay. Then it's very hard. Okay. Well, did you do your bachelor on also on? Okay. Are you familiar with electromagnetism, for example? Are you familiar with the BH curve?
No.
It's one of the constitutive relations of Maxwell's equations. We'll talk offline. I'll try to find a model that you know about it. We'll talk about that. But you can be sure about something like Maxwell's equations. I mean, we're pretty sure that they hold. But when you try to apply them on a complicated material like a steel that is produced in a specific way, that steel has magnetic properties that are different. I mean, steel of type 1 has magnetic properties that are different from steel of type 2. And maybe if there is a little bit of heterogeneity, the magnetic properties may change throughout the steel. All right. So even though the Maxwell's equations hold, there is somewhere in the Maxwell's equation something that changes over space, which we typically assume in courses that because we either look at void space or air, which they're both homogeneous things. We don't really care about this thing being uncertain. For example, that epsilon that appears may be a function of space and you may be uncertain about it. Okay? So that's a physical quantity about which you may be uncertain. This HB curve, look it up, it's something about the physics. All right? It tells you how the material responds to a given magnetic field. This is a constitutive law about which you may be uncertain. As a matter of fact, we don't really understand how to get correct HB curves from physics in the first place. Or in the molecular dynamics example, look at that. This is instructive. Yeah, I'll go over this again. So if you look at this example, we know that the physical law will look like that. It's the Boltzmann distribution, but this V over there, we're going to have to guess it. Does that make sense? We're going to have to guess it because getting it from first principles is next to impossible. It's computationally impossible. So at some point you have to make a leap and say something about it, and you're going to have to be, you're going to be uncertain about it. Okay, and you better keep this uncertainty and propagate it through anything you do. Questions? This is extremely important. I mean, it's more important to understand and appreciate these uncertainties than actually learn how to deal with them. Yes?
So you said for getting the potential energy, we have to calibrate it with some measurements that we have.
Yeah.
And we cannot use in a different type of system, right? That's what you said.
So here's what's going to happen, okay? Because calibrating empirical potentials for molecular dynamics is extremely difficult, if not impossible. Because, so here's what's going to happen. If you calibrate this model to a specific data set and it matches it perfectly, and then you take it and you try it at different temperatures, it's not going to work. I mean, obviously, if you try it a little bit, a few degrees Kelvin next to the temperature you calibrated on, it's going to work. But if you change it dramatically, it's not going to work. If you try to predict when a material melts, for example, it's not going to work if you have calibrated for the solid state. If you start pressing the material and you try to predict with this potential, it will probably not work. If you mix this material with something else, it will probably not work. If you start adding dislocations or crazy stuff or foreign bodies inside this thing, it's not going to work.
So if you are introducing uncertainty into this model, then we can get out a model which can work for all this.
No, this is not what I'm claiming. I'm on camera. Because this is a very hard problem, okay? But what I'm saying is that if you, instead of calibrating a model by picking the parameters exactly, like picking a value for the parameters and having a concrete model, perhaps you should think of a model that has a little bit of uncertainty, so that instead of exact predictions, you get error bars, and maybe that can be calibrated better. And it can give you more transferable results. Okay, but this is an extremely hard problem. If you want to waste 2 years of your PhD, start working on one of these. It's seriously. All right. So, let's start now talking about probability measures on function space. All right, we have a function. We're uncertain about that function. It lives on a function space. We said that whenever we have an uncertain quantity, we should come up with probabilities for that uncertain quantity. Let's do exactly that. Let's go to the function space and put a probability measure on that function space. So the simplest such probability measure is Gaussian, okay? It's a Gaussian probability measure. It will, on a function space, and we'll define that precisely. And as usual, what we're going to be doing is first we're going to assign a prior probability measure that captures everything we know about these functions. And there are things that you know about those functions, and I'll tell you how you can describe them. And then, if you have some data, for example, some observations of these functions at some points, you can also condition on that, right? So if you want to come up with a model about the porosity of the ground from the oil reservoir problem, you start by putting a prior measure on the space of porosities, but then you can drill, for example, and measure the porosity at a bunch of points and condition your random fields to go through your measurements at these points. But we're going to do that in the next lecture. And it turns out that even though we motivate that from physical applications, you can actually use this idea to also do regression. So you can actually go and whatever we did with in the previous 3 lectures, you can actually do pretty much everything with these tools, with Gaussian processes, and it will actually work better. I will explain why in 3 lectures. So this is the mathematical definition of a Gaussian process. If you want the full mathematical definition, you should start by let omega be a sample space, F be a sigma algebra, P be a probability measure, whatever. Okay. And then this is the definition of a Gaussian process in this space. I'm going to read it. A Gaussian process is a collection of random variables such that any finite number of them has a joint Gaussian distribution. Okay? But in order to understand this phrase, I first need to tell you what is a stochastic process or a random field. Okay? And I'm not going to do that. I'll try to do it in a simpler way, so forget about this. Okay? I'll use this definition, but we're not going to worry too much about it. So it turns out that if you define Gaussian processes like that, there's a theorem called Kolmogorov's theorem that you can use to prove that there actually exists mathematically such an object that has these properties. Yes. So here's how it goes. We are uncertain about that function f, okay? So think of that function f as getting some inputs x and spitting out some outputs y, okay? So we treat f as unknown, and of course here unknown means uncertain or random, right? And we're going to describe f using probabilities. So we're going to write something like this. F itself is a random variable, okay? But it's not really a variable, it's a random function. Random functions are typically called random fields, okay? But they are also called stochastic processes. If the input is time, we usually call them stochastic processes. If the input is space, we usually call them random fields, okay? But the input can be anything. Could be space and time. You would also call it random field, or process, stochastic process. But it could also be space and time and a bunch of other things. And it will still be called a random field, okay? Now, this is abusing the notation, all right? Saying that the function is distributed according to a probability density. This is not really, doesn't really, I mean, if you really think about it, it doesn't mean anything, okay? But we will define things around them so that it works out fine, even though mathematically it's not very sound. Okay, but if we wanted to be sound mathematically, we would just spend, I don't know, 1 lecture talking about what random fields are. And then another lecture proving Kolmogorov's theorem. And then at the end of the class, we will talk about Gaussian processes, perhaps. Okay? But we're not going to do that. Anyway, so we see this and we read, the function f is uncertain and it is distributed according to some probability law. And what I will describe today is that probability law. Okay? So, that probability law will, I mean, it's called the Gaussian process, and will tell you what it needs. It needs two ingredients to define a Gaussian process. You need two ingredients: a mean function. Just give you the names first: a mean function and a covariance function. Two things: mean function, covariance function, and they are actually functions. Okay. And now, in analogy to the multivariate Gaussian, in the multivariate Gaussian, what did you need? You need a mean vector and a covariance matrix. Well, now that you go to a Gaussian and a function space, you need a mean function and a covariance function. That's the analogy, right? Okay, so you use the mean function and the covariance function to define a probability measure on a function space. Just like you use a mean vector and a covariance vector to define a probability density on a vector space. And we're going to write this. So we'll say, our function f is uncertain, and we write that this uncertainty here, which corresponds to the definition of the random field, that random field is a Gaussian process. This is basically the variable that goes with that Gaussian process, okay? This is the mean function, and this is the covariance function. Okay, mean function, covariance function is just the label we use. And we read, we believe that the function f is a sample from a Gaussian process with mean m and covariance function k. That's what we read. Well, this doesn't give you a specific density for f, because a density for a function is completely meaningless, but it means something very specific about the function values at different points, and we'll talk about that in a while. Okay? Any questions about this? Yes.
So the function in itself, is it just one function, or is it n-dimensional function like f1, f2, fn?
It is a function. You should think of this. So the function here does not really exist, in the sense that there's a function space. Okay, the space of functions from R to R, for example, right? It's a space you cannot really visualize, especially by doing this with your hands. Okay, but imagine it. Okay. Now this thing defines a probability on that space, right? What we saw before was we took the real line and we defined a probability on the real line, okay? Now imagine that real line, each point on the real line is a function, and we define a probability measure on that. It's a little bit strange, okay? So this tells you that this is just the definition of that probability measure. The way you should think about it is as follows: that f is something in your application, something in your physics. It's a function of space. It's a function of time. It's something, and you are uncertain about that something. So here you say, I am uncertain about that something, and I believe that it is a sample from this probability measure. I believe that it could be a sample from that probability measure before I see anything else related to that. Yes?
I think the dimension of the function space is greater than 1.
The dimension of the function space is greater than infinity. It's infinite.
The real line to represent all the functions.
I don't. This is a metaphor. I cannot represent these functions in one in the real line or in two real lines. It's impossible.
So what distribution is it?
We will talk about that. Okay. Now I'm just telling you the names of stuff. Okay. So I haven't really told you what this thing is. This thing is defined through what is known the finite dimensional joint distributions on different points. We'll talk about that. Okay. One by one. One by one. Other question?
You actually answered. So I was trying to ask, is the functional form absolutely uncertain, or is it that we know sort of the functional form, but then when we predict the values at each point, that is uncertain.
Yeah. So this is a great question. Here we're basically saying that we don't know the functional form at all. Okay? You will see in a while that this tells us something about the function, the mean tells us something about the function, and that the covariance also tells us something about the function. You will see this in a while. All right? All right. So what does the mean function tell us? So the mean function responds to the question, what do you think fx could be? Okay? So somebody puts a gun on your face and they tell you, you are looking at x, what is f of x? Pick a number. Okay? It's the answer to that question. And it's the expectation of f of x. Okay? So whatever that probability measure is on the function space, if you look at one point, if you take the function at one point and you look at its value at one point and you take the expectation of that, you're going to find m of x. Okay? So this is how we're going to define this probability measure implicitly through these things. Any questions? So if you have some beliefs about the trends of f, you can build them in there. If you think that a particular model may be good for f of x with a specific functional form, you can put it in there. Okay, so model your expectation about f of x. So now, somebody asks you, all right, so if I force you to predict at f at x, you will give me the expectation. What do you think about the uncertainty? All right, so how uncertain are you? So the covariance function, one of the jobs of the covariance function is to quantify this uncertainty. So if you take the covariance function, so the covariance function is a function of two variables, x and x prime. If you evaluate it, you evaluate each one of its inputs, if you set each one of its inputs to x, then what it gives you is the variance of that function, of the function at that point. So if somebody tells you, all right, so go to x and draw an error bar around what do you think x could be, okay? 2 times the square root of that should be that error bar, okay? Intuitively, this is what it means. Yes?
Where is the expectation taken?
The expectation is taken over the random field, over this thing that I haven't yet defined,
Yes.
over the probability measure on the function space.
How do you take the integral on an infinite dimension space?
You will see. Okay? You will see. Hang on. We're going to do it without measure theory. So you will see the intuitive way of doing it. All right, so this thing will quantify your uncertainty about f of x. All right, and the average is over all the functions, all the values, all the possible functions that you could have. It's an average over that. Okay, it may seem strange, but it's very, very well defined. I just didn't want to start with this because perhaps only 2 or 3 people would appreciate that. And that would be the mathematicians, if you know what I mean. Okay. Yes.
Assuming f as a probability measure of Gaussian process, is it an assumption? Like we are assuming f is a Gaussian process.
Yes.
So is it an assumption? I mean, does it happen in reality for all the?
It is okay. So the question is, you are assuming that your uncertain quantity is a Gaussian process. Does that uncertainty correspond to something in reality? The answer to that is not necessarily, because this thing, we use it to describe our state of knowledge, right? And not something that, not a physical property, okay? The function about which we're arguing may be a specific function. We just don't know it, okay? And we're modeling our state of knowledge about it.
So is it an assumption that we are seeing it as a Gaussian process, or Are we modeling the function?
We're modeling our uncertainty about the about what that function is using a Gaussian process. Is this a good model? Of course it is an assumption. Okay? Is it a good model? It is the simplest model. Okay? Therefore it is a good model to start with. Alright? So, we talked about the covariance function at a given point. Let's talk about the covariance function at two different points. So now somebody asks you the following question. You are looking at the function values at x and x prime, two different points. And I ask you, how close do you think the corresponding outputs are going to be? Okay? Just give me a number. If you tell me 1, they are close. If you tell me 0, they're not very close. And of course, as I bring x and x prime closer together, you should probably expect the function values to come closer together, right? As you take x and x prime further apart, you should expect the function values to become decorrelated. Okay? Now, this effect is modeled by the covariance function. That's what the covariance function models. The covariance function models the similarity between the function values at two different points. This is what it models. And it is defined as a covariance over the random functions evaluated at two different points. Alright, so to wrap it up, we're going to be writing this, and we will be reading this function, and we're uncertain about that function f, and we model this uncertainty, which is uncertainty in our state of knowledge, as a Gaussian process with a specific mean and a specific covariance function, and we interpret the mean as what we think the function value is. If somebody pushes us to pick a value, that's what we would pick. We interpret kx, x, the covariance function evaluated at the same point, as our uncertainty about the function value. And kx, x prime, the covariance function evaluated at two different points, as the similarity of the function values at these two different points. Make sense? Alright. So I'll show you now the simplest, the most common covariance function. It's called the square exponential, and we'll explain this a little bit. So you see what it is. Let's look at its form. It has a v there, and then takes the exponential of the difference of the two, of its dimension of the two inputs, scaled according to something, squared. Okay? So this v over there, is actually the variance. It calculates your uncertainty about, it corresponds to how uncertain you are about the value of f of x, how far away it can be from the mean. And you can see that, if you set at both inputs x, this is going to be 0, exponential of 0, 1, you're going to get that v. Okay? Now, this L is called a length scale, and it models the similarity of specific input dimensions. So it tells you basically how fast your function changes in a specific direction. If you have a big L, then your function changes very slowly. If you have a small L, then your function changes very fast. So by choosing this L, you can encode this information. And we will visualize that in a while. Alright, so this is how this covariance function looks like. If you evaluate it, if you fix its second input, let's say to 0, and you just change the first one, right? So now you see the covariance as a function of only the first input if the second input is 0. So you're basically looking at the similarity of the function value at 0 to the function value at any given point. So you see that for big length scales, you're getting, for big length scales, you're getting this. For very small length scales, you get a covariance that is more sharp. Okay? So as you start increasing the length scale, the covariance spreads out. And basically what you read here is that the bigger the length scale, the more correlated the function values are. The more you know about what is happening in a neighbor of a point if you have observed the function value there. All right. Now we will start introducing a little bit of the math, okay? This is how everything is defined. It is defined through distributions on it's defined through the function values on a finite set of input points, but arbitrary finite set of input points. So go to the space of inputs and pick any points you want, n such points, okay? These guys right there. And now think of the function values on these points. If this f is uncertain, then this thing here is a random vector, okay? Now we are actually defining the Gaussian process, which is a probability measure on f, by defining a probability density on all possible finite dimensional distributions like that, on all possible finite dimensional selections. This is how it is defined, okay? And if you define this in a consistent way, and consistency here comes from Kolmogorov theorem, then there exists such a mathematical construct called Gaussian process. Okay? So, let's define the covariance matrix real quick. So we're going to define the covariance matrix of the function values at these arbitrary points like this. So you see that this is the covariance function evaluated at all pairwise combinations of the points, of the input points you have selected. Okay, all pairwise combinations. One with 1, one with 2, one with n with 1, down to n with n. Okay, all pairwise combinations. So this is what? This is gonna be the covariance of that random vector. Okay, this is nice and finite. So there we're gonna have to put some restrictions for that in order to be mathematically sound. We need to put a little bit of some restrictions on the covariance function itself. So we would like to pick a covariance function that is positive definite in the sense that no matter how we construct which covariance matrix we construct, in the sense that these x1s and xn's are completely arbitrary now, this covariance matrix must be positive definite. Do we all know what positive definite means for a matrix? The eigenvalues must be positive. Okay, that's what it means. If the eigenvalues of this matrix are positive for every possible selection of input points, then we say that the covariance function is positive definite. The square exponential is positive definite, and the only covariance function that you're allowed to use is a positive definite covariance function. Now, if you have one positive definite covariance function or one family, you can make other positive definite covariance functions out of them. So, for example, if you take two covariance functions and you add them together, you get another covariance function. So you can take k1 and k2 and make another covariance function. If this is positive definite and that is positive definite, then this is going to be positive definite. And this actually, it may sound ridiculous, but it actually corresponds to saying something about the function itself. So if you pick a covariance function like this, you're actually saying that f comes from two independent sources that are added up. It's actually a way to say this. Alright, so it's as if you're saying f of x is not really one function, it's two functions that we're adding together. The first one is this one, the second one comes from this covariance function. And this will allow you to model things like multiple scales. Anyway, you could also do this, multiply two covariance functions together, and it will still give you a covariance function, and this corresponds to saying that your function is basically the multiplication of two functions that are unknown. And of course, with that, you can make things that are as complicated as you wish. Okay? Now I'll show you how to sample from a Gaussian process. And then I'll let you play. I'll go a little bit faster. All right. So the Gaussian process defines probability measure over the function space. But how can you sample functions? Functions are infinite dimensional things. Well, you can sample them on a finite number of points. Okay? That's the idea. So you can say, okay, I give up. It's an infinite dimensional thing. I will sample it on a finite dimensional, on a finite number of points, on this point, that point, that point, and that point. Okay? So here's how it goes. You pick the points where you want to sample these functions. And then you consider the output on these points, f. This is a random vector. Now, this is the definition of the Gaussian process. The Gaussian process says that if you look at the function values at an arbitrary set of points, the function values are distributed according to a multivariate Gaussian with a mean vector that comes from your mean function and a covariance matrix that comes from your covariance function. This is how it is defined. So your problem basically, if you want to sample the Gaussian process, is to pick a dense enough design of points, build the mean vector, build the covariance matrix, and then sample from this multivariate Gaussian. You will see now some pictures, hopefully. Okay. All right, so we need to sample from that. This is how everything gets mapped down to finite dimensional things. Okay. So the mean is basically your mean function evaluated at these points. Covariance is your covariance function evaluated in all pairwise combinations. And then you have to sample from a multivariate Gaussian, and we have made this an exercise. And the way to sample from a multivariate Gaussian is this. We're skipping it, okay? You'll get the chance to do it, don't worry about it. But anyway, so now you will start seeing samples of a one-dimensional Gaussian process with a square exponential covariance, okay? First, I'm gonna start, these crosses that you're gonna see here are the points on which I am sampling the function. So initially, you're not really gonna see a function, but I'm gonna start increasing the density of these points, and then you will start seeing functions, okay? So because I didn't wanna do a static picture, I did the following thing. I take a sample on the function space, and then I define a closed loop on the function space, and I'm going around this closed loop. So you will see a video, all right? So here's how it looks like. So you see with 5 discretization points, 10, 20, and they start looking like functions, 50, and they are very, very smooth functions, okay? So you see that this is how you approximate probability measure on a function space. With a finite dimensional function evaluations, which you increase their number more and more and more, okay?
Why are they shaking?
They are shaking because I wanted to make a video out of them. So in reality, all right, its frame of this video is one set of samples, right? Its frame is one set of samples, right? What I'm doing is I'm going to that function space. I go to the function space. Here's the function space. I go there, I take a sample, and then I draw a circle in the function space, and I move around that circle to give you that wow factor. Okay? And I do that, I do this for one function, I do this for another function, it goes like that in that function space. That's what you see here 3 times. Okay? The blue line is the mean. Okay, now let me show you what happens if you if you do this in 2 dimensions. Right, in 2 dimensions, obviously you're gonna have to sample on a grid. So if your grid is very coarse, it doesn't look like a function. But as you make it finer and finer, it looks like a function. Okay? And again, here it's a one sample, moving on a closed loop, just for presentation purposes. Okay? So this, for example, could be a random, a stochastic model for a quantity that is a function of space, right? That could be a nice model. Like the initial conditions for the numerical weather prediction model, right? What is the temperature? I don't know what it is. Let me just make it be model it like that.
Are we giving any bounds for the
So this is a very good question. Very nice. So these f's move up and down, right? But they are moving within specific bounds. These bounds are specified by this v parameter, the covariance function. Whatever multiplies the covariance function tells you how much they're gonna move up and down. Give these bounds.
So the user has to select the locations, the grid points and the bounds on it.
Yes. So this is a good point. You're gonna have to. I'll tell you. Let me finish with this, and I will tell you in detail. All right. So let me now show you the effect of the choice of length scale. Okay. So the covariance function had the square exponential covariance function had one parameter, the length scale. Right. So if you start decreasing the length scale or increasing it here, I start from a very small length scale and then I make it bigger and bigger. You can see the length scale over there. For small length scales, the functions are very, very wiggly, and then the bigger the length scale, the smoother the functions become, to the point where for a very big length scale, they become almost straight lines. Okay? So what is the right choice of length scale is not something that I'm concerned with, because that depends on what you think about that function as a practitioner. Okay? But I'll give you the idea to describe a way to describe what you have in your mind using these tools. Anyway, now another thing that I want to show you, and again proving this, it's not really for this course. I want to show you that the choice of the covariance with the choice of the covariance function, you can basically choose the regularity of these functions, like how smooth are they. So if you choose a square exponential function, you're basically saying, I believe that this uncertain function can be differentiated an infinite number of times, and at each time I get a continuous function. Continuously differentiable infinite times. Corresponds to this belief. There is actually a one-to-one map between the choice of the covariance function and the regularity of the samples you get. Basically, the samples you get are going to be as regular as your covariance function. So you can do things like, for example, if you pick a covariance function like the Matern covariance function, which is 2 times differentiable, it doesn't have third derivatives, then your samples are going to be 2 times differentiable. They're going to be less smooth than the other ones. And maybe that's what happens in your problem, right? Maybe in your problem functions look like that. Maybe you can take 2 derivatives and then things go sour, okay? Or maybe in your function is continuous, but cannot be differentiated anywhere. Kind of looks like a fractal, right? Then you can pick a covariance function like the exponential covariance function, which has exactly this property. It is continuous, but you cannot differentiate it. Therefore, the samples you get will be continuous, but nowhere differentiable. But of course, you cannot really see that they are nowhere differentiable, because I would have to use an infinite number of points for you to see it. Okay, but you see that they're going to start becoming a little bit strange when you increase the density. And of course, I mean, you may wonder, is this a good model for example, stock prices? Not really, because stock prices are not even continuous. So you need also to break the continuity property. And then you can do that by picking a covariance function that is not even continuous, has to be like a delta function, okay? And then you get a Brownian walk. This is how the process would look like. But it would not even be continuous, okay? And it will have other strange properties. You can spend the semester just studying one of these covariance functions. Like so, for example, that if you, I'm not gonna say it. Forget about it. Okay. And you can do even crazier stuff than that. I mean, you can make, you can put a probability measure in a function space, the samples from which are periodic functions. If you make your covariance function periodic, the samples will be periodic. And you can do even crazier stuff than that. You can actually pick a covariance function that satisfies specific physical laws. You can say, for example, give me a function that satisfies an elliptic partial differential equation on that domain. Give me samples from that. You can do that as well. It's a little bit more difficult. Anyway, we have 8 minutes. That will give you the chance to pull the notebook and play with it. In the notebook, I have all the details, including the definition of the Gaussian process, the mathematical definition of the Gaussian process. Feel free to skip through all the details and go down to the point where you start playing with the covariance functions and where you start taking samples of Gaussian processes. So if there's one thing that you need to do in this handout is one, look how GPy works and take samples of Gaussian processes. That's pretty much it.